our YouTube file, our YouTube video file will be two parts, part 1 and part 2, because I was out of space. I don't know if I'm out of space for some reason. So this direction is the backward direction. Okay, this direction is the backward propagation direction. And from the backward direction, I get the upstream gradient. Okay, and I feed it to the downstream gradient. What I do in between is to take the local gradient, okay, inside this function. See an example, okay. I got this derivative of s with respect to h, but h depends on s, okay. So I take h depends on s, so I take this derivative of h with respect to z, okay, and I pass along this derivative down. Okay, so that's what happens with the chain rule. I get this, I multiply it with this one, okay, this will calculate that one. So if I do it this way in this order, I can go to all the way to the beginning of the network, and any parameter changes, I can know how it is changing the score function. Okay, so each node has a local gradient. Each node has a local gradient, and I am responsible for taking the local gradient of the node. And I showed you how to do that, okay? How to do that. Taking the gradient inside this f is simple because f is a nice continuous function. This is local gradient. And this is what comes to me from the upstream gradient, and this is what I had out. So this was a simple case because one input and one output. Sometimes I have this kind of stuff. I get W from some place and I get X someplace and I multiply them and I hand it over. Okay. So forward pass is easy. Okay. Forward propagation is easy. Multiply this one with this one and output at this one. How about coming backwards? How about coming backwards? Okay. What am I gonna do? So what I do is, okay, I get derivative of score with respect to z. If I'm going to go this direction locally, okay, my z depends on x. So derivative of s with respect to z and derivative of z with respect to x. So this is what I'm going to calculate. And in this case, I'm talking about the w's. Okay, I am going to talk about the w's. So when it comes to this kind of multiple inputs, this is how you would continue. This is how you would continue. Okay, so this slide set has a nice example. This is not this graph is not about neural networks, but it's a very simple function. This function has 3 inputs, and function is like this: x plus y times maximum of xy. Okay, and for the x, y, z values, I got these. Okay, these are the inputs. Okay, so let's try to draw this diagram, this graph. Here is my graph. Nodes are operations, edges are the data. At the beginning, my inputs are the nodes again. Okay, so this one is going to be x plus y, and this one is going to be maximum of maximum of yz, and this time is going to be the multiplication of these two. So this one is going to be x plus y times maximum of yz. Good. Okay, so we are going to do some derivative stuff. We are going to take the derivative with respect to x, y, z. Okay, so if I put these inputs 1, 2, 2, 0, 6 is the result. Okay, so if you put 1, 2, 0 to f, 6 would be the result. So that's fine, no problem here. So let's take the local gradients. Remember what we were doing here? Taking the local gradient. This is plus, okay? This one is a equals to x plus y. Let's take the gradient of a equals to x plus y. Okay, let's take the gradient of a equals to x plus y with respect to x and with respect to y. So if you take the gradient of a with respect to x, it's going to be okay, y will go away and I will have x, and if I take the derivative of x with respect to x, it's going to be 1, and again similarly derivative of a with respect to y is going to be 1. Okay, so that is the local gradients of this node. Okay, local gradients of this node is going to be that. Okay, let's take the local gradients of this node. Does anybody know how to take the local gradient of this one? Max xy, xz. So I am going to do this. Derivative of b with respect to derivative of y, and derivative of b with respect to z. X is not relevant here because I don't have x in this node. Do you know how would I take the derivative of b with respect to y? I will give you a clue. Hint. Is this, well, maybe you don't know what this is. This is a curly bracket. So it's a partial function.
Can we just do derivative of y if y is bigger than c, and otherwise?
Yeah. So there, it's not, I mean, it's not derivative of y. What is derivative of y? It is 1. Derivative of y with respect to y is 1, right? If it is 1, if y is greater than z, right? What happens if y is not greater than z? Then 0, right? Okay, so exactly the same thing with the b with respect to z. It is 1 if z, y, if it is 0, z less than y. So something like that. So I know the local gradient of this one. Then I am going to calculate the local gradient of this one. Okay. So yeah, like what I did. Let's look at the local gradient of this one. Local gradient for this one is easier, right? Why? Because if I take the derivative of f with respect to A, then B will stay, and derivative of f with respect to B is A. Okay. So I can calculate all these derivatives because I know x is 1, y is 2, and z is 3. I know the input. Okay, let's look at this one. What does this one say? How does your f changes if I change x a little bit with respect to x? That's it. Okay, so this one talks about the a change in a with respect to x. But what I am trying to do is how does my output function changes with respect to all the input parameters. Okay, that's what I am trying to do. For that I need to use the chain rule, right? Multiply all of them. So I am going to multiply how the f changes with respect to a, then how the x changes with respect to b. Okay, so I am going to multiply it and I will get the results, and that will be, so this is expected. What does it say? This one says that, okay, if I change this a little bit, your function will change like 2 and like 3. So go all the way. So how did I do this? 1 times 2. What is 2? 2 is the derivative of with respect to a, this one. And this one 1 times 3. And continue this way. Okay, this one is 0. Which one is 0? It is this one. Derivative of b with respect to z is 0 here. What does this one say? It's interesting. This one says that change z a little bit. So you complete my sentence. Change z a little bit. Your function f complete my sentence. Change z a little bit and your function f ... Will not change at all, right? Because it is 0. But this one says that change y a little bit and your function will change, will increase like by the amount of 3. It is not negative. Okay. So do the same thing again for the others and we get these results. Of course, in our, again, this is not a neural network. This is just a network. Okay. In our neural network, we are not going after changing our inputs. We are after changing our parameters. How should I change my parameters so that my loss function decreases? I will get closer to 0. That's what I'm trying to do with the back propagation. Okay, by the way, here is another thing. So y is connected to 2 places. So what am I gonna do? I get 2 here and 3 here. So change y a little bit. I will get 2 changes here and 3 changes there, and total is 5. So it looks like changing y has the most effect on the output. Changing z has no effect. Okay, any questions? Okay, so I think we have seen this. Did we have any? Okay, so with the y I have this, right? Let me put them together. Y branches out of a branch. When the back propagation comes from one side to the other side, I add them together and back propagation goes. Okay, so this is gradient summit branches like that 2 times. Okay, I did that. What else? So this is nice. When plus comes in, plus distributes the upstream gradient into each segment. Okay, so as you see, I get this 2. Okay, and I distribute these 2 here and there. That's what 2 does. Okay, what does the plus does? The plus operation does it that way. It gets these 2 and it does it that way. How does it do that? Okay, it does that. It does that. By, let's go and find out this plus. Okay, so I get this 2, and for the plus is a, right? So derivative of a with respect to x and derivative of a with respect to y is 1 and 1. So I multiply these 2 by 1 and 1. Okay, it is 2 and 2. So I just copied it to all the branches, so it is distribution. So this one gets it and this one distributes. How about the multiplication? What does the multiplication do? What does the multiplication do? It gets 1 and it does something. Okay, so plus distributes. What does the multiplication do? Multiplication. Okay. Oh, this one talks about the max. Let's go to the multiplication. Multiplication says that I am going to switch the upstream gradient. So 3 is going that way, 2 is going that way. Okay, and max is rerouting it. Okay, with the max 3 goes either this way or that way. It is rerouting it. Okay, good. So this is how we do the back propagation. All the calculations are there. Okay, so for each node I have an upstream and downstream, and multiply upstream by my local gradient, and that's how I calculate stuff. Good. So I don't want to spend some time. I mean, these are important, but I don't want to spend much time on it. Let's look at this one. Calculation of derivative with respect to b and calculation of derivative with respect to w are very similar. They are similar up to this point. So if I am calculating both, there is no point in calculating them separately. So calculate the common part first, then multiply them with the remaining later. Okay, so that's the correct and efficient way. So I'm going to skip these parts, and I think, no, well, I mean, with all the deep learning libraries, when you make these kind of, okay, this is a better example. With all the deep learning libraries, when you design these kind of networks, okay, those libraries will help you do the back propagation, do the training. All you need to do is provide this local gradient. Okay, let's look at this node. The node says that multiply x and y and produce z. Okay, that's the forward propagation. With the backward propagation, I need to provide dx and dy, and this code will be written by you here. What is your local gradient? Find the local gradient. It is not that difficult, because if I take the gradient of x times y for x, I know that it is just y, okay, and just the opposite is x, so I know what to write in here, okay. So it is just for dx it is just y, for dy it is just x, and I could return it, okay. So the code that you write is just for the local gradient only. Back propagation part, all the multiplication and everything, all the efficient calculations will be done by the deep learning library. Okay. Good. Any questions? If there are no questions, by the way, do any of you remember this formula? Taking a numeric gradient of a function. Do we use numeric gradients in any place in our networks?
Depends on the implementation. For
What
example,
do you mean?
TensorFlow uses symbolic gradients. PyTorch uses something called auto gradient, I think. And it's numeric.
But do we need to use them?
No, we can do symbolic.
Because all of my nodes are analytically defined nodes, right? It is either multiplication or max or plus, that kind of nice stuff. I can take the local gradients symbolically, okay? But some tools, they prefer using these kind of numerical approximations, and there are some very nice speed up techniques for it. Okay, so that's good. So at the end, what did we do? At the end, what did we achieve? We achieved this. Let's go to the network. Let me find my, okay, my network is I'm trying to find my network. Okay, my network is this. It will take a input of 20 numbers that will represent words like museum in Paris are amazing. Of course, obviously a toy problem. Okay, and I will feed them to this eight logistic regression units, and then the result will be multiplied by this U vector, and it will produce me a score. Okay, and this is going to be my neural net. Since I have this middle layer here, this can represent non-linear relationships between the inputs. So I say that maybe I can handle the complexities involved in the natural language processing. If one layer is not enough, well, it should be enough for most cases, then I will add more and more layers. Okay, the theory says that if you use enough number of nodes in the hidden layer here, you could learn everything learnable. Everything learnable can be learned if you use a single hidden layer. But we keep saying that the deep learning uses many layers, up to 100 layers, right? So why do we use many layers? One of the advantages of using many layers is that such networks are very generalizable. You don't depend on your input only. Okay, you don't depend on your training data only. New data that you're gonna find later is going to work good on your network too. Okay, so up to now we played with this toy problem of named entity recognition. Named entity recognition is not a toy problem, but we made it a toy because our vectors are 4-dimensional, and this network is too simple. Okay, let's look at something more practical and more real life like. Okay, that's going to be that's going to be where is it? That's going to be our RNNs. Okay, so language models and neural networks. Okay. Before we continue, let's look at some of the details of optimization. Remember our loss function? Loss function says that I am going to optimize this. By the way, why do I keep doing the same thing? I mean, we are not using this Softmax anymore, right? We have a neural network. Why do I keep optimizing this now? Don't see the second part. That's not relevant for now. Our formula did not change, right? I mean, this was the formula for the Softmax based classifier. Now I started using this neural network which has many layers. I still keep using the Softmax. Why do I using the Softmax? In our original version of FYI, what was FYI? Do you remember? It was WI times X, right? So that was the original one. This one is kind of different. What is the meaning of FYI for our neural networks? It is not WI times X anymore. What is FYI?
Is it the prediction of the model?
Prediction is going to come from the softmax. Well, of course, this is not softmax. This is the loss function, but loss function uses the softmax, right? Prediction will come from the softmax. But what goes in the prediction? That's what I am asking.
The probability of our given input is that in that class, I think.
That's what softmax calculates. That's what softmax calculates. Probability of given input being in that category or class. But
okay.
what goes into this softmax? What is FYI? Let me try to go back.
Only the probability of happening of that instance happening.
Let me go to the beginning. Is this the beginning? Oh, I went too far. I think I will look at this one. Yeah. Okay. So this was the softmax classifier. Given the input, what is the probability of being in class Y? That was the original. But we are not using the softmax classifier anymore by itself. What did we say? Softmax classifier by itself Okay, Softmax Classifier by itself alone not very powerful. We had to do some stuff, so we added these neurons like that. Okay, so before the softmax I have these. So what is input to the softmax is the output of these neurons. Okay, so output of these neurons will be the input to the softmax. Okay, so these will be FYI will be the WI times the output of whatever I had before that layer. This part is called the regularization term. Just try to remember what is this? This is a minimization problem, right? This is a minimization problem. And they say that try to make this as small as possible, right? Make this whole red thing, well, it's not red. Make this whole red thing as small as possible. So it looks like the first part is about our softmax decisions. Try to make the correct class probabilities as large as possible so that negative log is small. And then, what is this? Take the square of each of the parameters and make them what? Read this for me. What does it say? Lambda is just a constant. Read lambda as like 1. Ignore lambda. It says that take all the parameters of the system neural network and
sum all the weights of squares of the weights.
so what does that mean in English? Why are we doing this? What I mean, no. Don't try to understand why are we doing this. What are we trying to achieve? Sum of the squares of all the parameters, and remember this is a minimization problem.
Maybe we are trying to minimize the parameters to I don't know, maybe for sparsity.
Salman, I did not understand what you said. Repeat again.
Since we are summing all of the elements in the loss function, then we are trying to minimize them too.
Yeah.
With some coefficient.
We are trying to minimize the squares of them. That means it doesn't matter if it is positive or negative parameters. We like them all to be close to 0. Okay. If I didn't have this part, if I didn't have this green part, okay, if I didn't have this green part, making all the parameters 0 would make this loss function very happy, right? It would be the smallest possible. You cannot make any smaller than 0, especially with the squares, right? But I have the green part. So this one says that whatever you are doing, okay, minimize this loss, pay attention to the correct classifications, but also try to minimize the make the parameters small too, so that don't go away from around 0. Do your minimization around 0. This is called the regularization over all the parameters, L2 regularization. Okay, this regularization kind of constrains your parameter space so that you don't overfit to your training data. Okay, it is shown to be very useful, and regularization is used in many places. and it is shown to work very well. Remember, this toy is very nice toy. Play with this toy. Okay, let me try to do. Okay, let's try to do this again, and say that I am going to use the sigmoid as activation function. Regularization is L2 regularization, like that one. Okay, and regularization rate is, okay, this regularization rate is the lambda in front of it, that one, and do this. It's going to make your, okay, smoother boundary lines. Okay, and it will generalize much better. So the loss and test loss are similar. It is doing very well. What is the problem? Why don't I get the perfect zero training loss? Can you guys see the error? Where is the error? I don't see the error.
Maybe it's because of the parameters aren't all zero.
Yeah, the regularization is contributing some. That's why I'm not getting. Okay, so this is not accuracy, this is loss. Right? This is not accuracy, this is loss. Also, there are many things that these systems are trying, like the dropouts and that kind of stuff. Okay, this is one thing that we need to be aware of, regularization. Okay, and this is not the only way to regularize stuff. Okay, that's one thing. There are many other ways of regularization. Other way of regularization is a dropout. Dropout is very funny. Okay, I mean, if somebody told you this, you will make fun of them for the network. They say that ignore 50% of your inputs to any neuron when you are doing the back propagation. Okay, just randomly set 50% of the inputs, each neuron to 0 at each iteration. Okay, this is what you're going to do. So you are not choosing the same 50%, but you are choosing the different 50%. Okay, so by doing this, it's another regularization method. You are preventing certain features are depending on each other, because some of them will go away randomly at different iterations. And it works. It works. It prevents overfitting. Okay. And sometimes in NLP we do vectorization, putting together all the words of different sentences together and optimizing them together. This one is good for performance, doing things in faster, sometimes 10 times faster. Okay. Another point in optimization is, up to now we have used this sigmoid, 1 over 1 plus e to the minus z, right? Sigmoid. How does the number, the e to the power, okay, but how does the e to the power, okay, this blue is 1 over 1 plus e to the power x, right? That's the blue. How about e to the power x? How does it work, e to the power x? E to the power, what is e to the power minus infinity? What is e to the power minus infinity? This is minus infinity. What is e to the power minus infinity? You guys don't know? Come on. What is any number power minus infinity?
0.
0. Exactly. So e to the power minus infinity is 0. What is e to the power 0?
1.
1. So it will come from here and it will do this, and it will start increasing like crazy and go away. Okay, So what is e to the power 1? What is e to the power 1? That is,
E.
yeah, it is e. Like this, right? So this is number e, and this is number 1. So this green is the function e, okay? The function e to the power x. Good. But how about this one? This one says that, okay, calculate this. When x is minus infinity, okay, minus x is plus infinity. What is e to the power infinity? It is infinity, right? So 1 plus infinity is infinity. 1 over infinity is 0. So this one, when it is minus infinity, is going to be 0 here. If x is plus infinity will make minus infinity here. E to the power minus infinity is going to be 0. So it is going to be 1 over 1. So for the plus infinity is going to be 1. How about 0? E to the power 0 is 1. 1 over 1 plus 1 is 0.5, and it is 0.5. So that's the calculation. So we like the sigmoid. Other than sigmoid, there are other activation functions. The other one is hyperbolic tangent. Okay, it changes from -1 to +1. That's the formula. Another one is hard tangent, h. So this is by partial, okay? It says that, okay, it is, you are always -1 if less than x is less than -1, and plus and x. This works too. But these two red ones have a very good advantage over this one. This one is very easy to calculate. These two are not easy to calculate, but these two have some very good advantages over this one. Can you guess why? Can you guess why? Why these two have advantages?
Do I have that quota still? So
No, Salman, we don't have quotas.
okay. Because after -1, the gradient is the same. In fact, it's 0, I think, and it might stop to learn.
So why do you think that that's important?
It's important to learn, I think, for neural networks.
Remember when we are doing the back propagation, what do we do?
The gradient?
Yeah, we take the gradient. How are you going to take the gradient of this function at these green positions? Right? Those are not differentiable. Those are not differentiable. So taking the gradient of this function is not that healthy, but still we do it. Anyway, whatever the advantage, disadvantages, nobody uses these three anymore. I kept using this one and that one. More modern activation units are like this. This one is used a lot. Rectified linear unit. That's it. This is a very, very simple function. It is max z0. Whatever your input is, okay, I will take the maximum of your input or the 0. So if it is greater than 0, it's just a linear, simple, the most linearest thing in the world. If it's less than 0, it is like that. Okay. So this one, again, differentiation at this point is bad, but I like to do it in two parts. If it is less than 0, the derivative is 0. It's constant. And if it is larger than 1, its derivative is 1. It's like max thing, right? 0 or 1. So it is very fast to calculate the derivative. And we will have some numerical stuff going on around 0. But we will ignore it. And it works very well. And in fact, with this tool, when I do this tool, okay, instead of activation, instead of using instead of using sigmoid, if I use the ReLU, okay, rectified linear unit, it works much better most of the time. See, I get these kind of effects. And with our gradient descent algorithms, the convergence is much better. Okay, let me move on. I know I am out of time, but let me finish this up. Okay. No, I am not going to finish up. I think I will continue next week on this. Yeah, that's it for today. Any questions? You will have 2 more homeworks. It will be about, of course, machine learning and NLP and deep learning and NLP.
Sure, can I ask a question?
Sure. So you were in the class?
Excuse me?
You were listening in the class?
Yeah.
Okay, I didn't notice. Okay.
This is the final week of lectures. Is next week gonna be the makeup lecture or?
Yeah, the next week is going to be the makeup lecture because I did not do 1 or 2 lectures. Okay, so one of the lectures I am going to spend on telling you about these RNNs, and I will do another lecture, but that lecture will be for the graduate students to do the presentation. They are working on their presentations, and that lecture will be only for the graduate students. Okay, but if the undergrads like to attend the lecture, they are welcome.
I see, thanks.
Okay, I'll see you tomorrow. I see you next week. What is the okay? I think next week Monday is the makeup date. Okay, whatever it is, next Monday I will do the lecture. Okay, see you next week.